Oh, hello. So at this point, you understand how to make, hopefully, how to make a two-way frequency table, how to take the categorical data, yes, I like camping, no, I don't like camping, and how many people said that, and put it into a two-way table. Hopefully you can also finish one if one is missing information. It's just adding or subtracting across rows and columns. Today we're going to look a little bit more about you how do you interpret the data from a two-way frequency table. So if you have printed this, you're going to fill in the blanks with me. If you didn't print it, it would be a really good idea to write this down because it has some key vocabulary in it that I'm going to say a lot in this video, and you want to write it down and make sure you've processed what I'm talking about. So a two-way table, just a basic two-way table, shows the frequency. And frequency is simply the number of times something occurs. How many times did people say, yes, I like camping? How many times did people say, I have blue eyes? So the frequency is simply the number of how often that happened. What we're going to calculate today is something called a relative frequency. And this really gives us a lot more information. Because if I say 42 people said they had blue eyes, your first question should be, out of what? 42 out of what? Because that really makes a huge difference. If it's 42 out of 42, that says a lot. Or is it 42 out of 1,500? That's a very different meaning. So instead of just a frequency, how many people said that, we can calculate a relative frequency by comparing that frequency to one of the totals. And as we've seen in two-way tables, that's probably the trickiest part of this, because there are many totals in a two-way table. So the hardest part about this today is making sure you're looking at the correct total. And how does changing the total you're looking at, how does it change the meaning of what you find? So you create a ratio out of something where you compare the frequency to the total, whatever total you should be looking at, and then you convert that ratio into a percent. Okay, and then that percent tells us a little bit more than just 42 people have blue eyes. 42 out of what? So on this down here, we're going to start looking at, I want you guys to focus on not only how to finish a table, but then as we start changing things into percents, how does changing the total that you use change the meaning of what you're finding? So an example down here, all these tables say, Josh is convinced that red cars get more speeding tickets than other cars. You guys ever heard that before? It's kind of one of those tales people tell, is that if you have a red car, you're going to get pulled over more, and you're going to get speeding tickets more. And Josh is convinced that that's true. So he gathered some data to find out. He asked people two main questions. He said, what color is your car? And he just divided it into red vehicles versus any other color. And he also asked, have you gotten a speeding ticket? Yes or no. So this two-way table starts putting together just the frequencies of the data that he got. So I can see from this that 45 of the people he asked had a red vehicle and also got a speeding ticket. 83 of the people he asked had some other color car and got a speeding ticket. And I'm missing the total on this row. So the first thing I'm going to do is add up those two numbers, 45 plus 83. When I'm missing a total or one of the marginal frequencies, I can just add to get that answer. And I'm even going to trace this like we talked about in the last video, where these values on the edge here, those are all of our possible totals, and they're also called our marginal frequencies. Now this overall total here, this tells me 128 people got a speeding ticket, 92 of them didn't. So already I can tell, regardless of the color of their car, that more people that Josh surveyed got a speeding ticket than didn't. Now I can add those up, and then I find out 220 is the total participants in this. That's everyone. He asked 220 people. Now here, if I have the total of red vehicles and I have the overall total, this again would be subtraction. So remember, when you're filling in a two-way table and you have some pieces and you're missing others, it's just like an add and subtract through columns and rows game of, okay, these two can add together to this. I know the overall total. I know one of these marginal frequencies, so I'm going to subtract again. So this subtraction tells me he asked 70 people to have a red vehicle and 150 people that have some other color. Now I'm missing these joint frequencies, and I'm actually going to change colors here so that I remember these ones inside are considered joint frequencies because they are the combined data. So this information over here is just speeding ticket or no, one variable. This information here is red vehicle or something else, one variable. This information combines both variables. 45 people with a red vehicle and a speeding ticket, and then 70 total red vehicles. So I'm going to subtract these, and I'm going to get 25 for my other joint frequency of people with a red vehicle and no speeding ticket. Subtract over here to get my other joint frequency of 67. And then I always just double check to make sure I didn't do any of my basic math wrong here. I add those across and I get 92, so I feel good about that. This table right here is just the frequencies. It is simply the counts of how many people have red cars, speeding tickets, other color, no speeding ticket. So what I'm going to do first, this first one asks me to change the whole table into percents. And when it says whole table percent, that means I'm using the total. I'm going to change all of these to a ratio out of 220, and then I'm going to convert that to a percent. So let's all make sure we remember how to do that. Grab whatever calculator you're using right now, and let's just start in this top corner right here. I'm going to do 45 divided by 220. You might hear hammering or sawing in the background. My husband's finishing the basement in the floor in our basement. So I did 45 divided by 220, got this value here. That is not a percent, that is a decimal. Remember, I have to go times by 100 and 20.454545. So I'm going to round everything we use in these tables here just so that I can make comparisons easier. I'm going to round to the nearest whole percent. So I'm going to put 20%, and I will use the colors I was using over there for marginal frequencies. That's 20%. Then I'm going to do the same thing with all of these numbers. All of these numbers I am dividing by 220, the total, the main total. So 83 divided by 220, change to a percent, is 38%. 25 divided by 220 times by 100 with 11%, and 67 divided by 220 times by 100 is 30%. And we'll talk about what those mean in just a second. Those are the joint frequencies. Okay, I'm going to come over here to the marginal frequencies now, and I'm still dividing all of these by 220. The whole table percent means I'm dividing it by all of the participants. It's a ratio out of everyone. So 128 divided by 220 times 100 gives me 58%. Then I did 92 divided by 220, gives me 42%. And this column right here, what do you notice about 58 plus 42? That adds up to 100%. Everyone, because 220 divided by 220 is everyone. That's 100%. So of course, this part down here is going to have 100% because it's everyone. Now across here, 70 divided by 220 times 100 gives me 32%. 150 divided by 220, guess what? Gives me 68%. There's the sawing. So that adds up to 100, and that adds up to 100. Do these add up to 100? Why don't these add up to 100? Oh, because they're joint frequencies. They're not supposed to add up to everyone. They're actually supposed to add up to their row. Oh, look at that. 20% plus 38% is 58%. 11% plus 30%. Ooh, that would actually be 41%. So why is that off a little bit? Well, it's because we rounded to the nearest whole percent. So if we'd rounded to the nearest 10th of a percent or 100th of a percent, we would have gotten a little more accurate there. But these columns also should add up, or at least get really close. You should always be within 1% because of rounding. You shouldn't be anything farther off than that. But what this tells me, when I divide like this, here's what I now know. I know a lot of stuff, actually. I know 58% of the participants have had a speeding ticket, and 42% of the participants have not. So I automatically know from this table that more people in this survey got a speeding ticket. Regardless of the color of their car, more people got a speeding ticket. I can also see down here that 32% of all of the participants had a red car, and 68% of them did not. So that's interesting information to know. In my particular survey, in Josh's survey, fewer people drove a red car. And these are important things to know if we're going to try and draw any conclusions from this. This number right here tells me 20% of everyone, 20% of everyone has both a red car and has gotten a speeding ticket. Now, is that enough to tell me, is that enough to say, yes, red car owners get more speeding tickets, or is it enough to say no? Is that percent high enough? Is that percent too low? Well, I think when it comes to joint frequencies, I feel like probably doing a percent out of everyone is not telling us enough, because we're concerned about whether red vehicle drivers get more speeding tickets. So what if instead of a whole table percent, what if we try a row percent? So I'm now changing my ratio, what it's out of. I'm now going to make it out of total people that got speeding tickets and total people that did not get speeding tickets. So let me show you what I mean. Across this row, I know 128 total people got speeding tickets. So instead of putting 45 out of 220, let's find out of the people who got speeding tickets, how many of those people were driving a red vehicle. So I'm not going to do 45 divided by 220. I'm going to do 45 divided by what? What do you think I'm going to divide by? If I'm only focused on this row, I am now only dividing by the number of people that got speeding tickets. So I did 45 divided by 128, and that gives me about 35%. It's a different percentage. So down here on my row percent, what I just found out is 35% of people who got speeding tickets also drive a red vehicle. That's what that's out of. I'm going to say that one more time. 35% of people who got speeding tickets also drive a red vehicle. Now, if I come over here, this one was 83 out of 128. I am sticking to this row. I'm focused on just that row. So 83 divided by 128 times 100 gives me 65%. And now because I am focused only on that row, guess what 35 plus 65 is? 100%. Because I was only focused on people getting speeding tickets. So now I see that 35% of people who got a speeding ticket drive a red vehicle, and 65% of people that drive any other car color also got a speeding ticket. So what is this showing us? No, let's do the next row. What if I focus on people who don't get a speeding ticket? So now I'm on this row. So you should never set up a ratio for a row or a column using a number that's not in that row or column. Do not use a number that's not in that row if you're trying to do a ratio. Okay, so I'm focused on just this row. Okay, so for the no speeding ticket row, we're now going to go out of 92. So if I want to find this percent, I'm looking at this row, and I'm going to do 25 out of 92. So go ahead and type it in your calculator. 25 divided by 92 times by 100. You should have gotten 27%. That just told me that 27% of people that have not gotten a speeding ticket also drive a red vehicle. Okay, and then when you calculate the other one, not surprisingly, it is 73%, because 27 plus 73 is now 100% for that row. And in fact, if we're doing row percentages, then the end of every row should be 100%. You might look at this and go, wait, that doesn't add up. 100 plus 100 is 200. And that's because we're only focused on rows. We are not focused on columns right now. So if I look at the total, I can still do a row percentage for this. I can say 70 divided by 220. I'm now looking at the total row. 70 divided by 220, I really already figured that one out up here, right? So that part's not really going to change. I've got 32% and I've got 68%. I still know that 32% of everyone drives a red car, 68% of everyone drives another color. But these are the ones that are a little more interesting to me now. That helps me look at this a little more closely. So the question that's answered here is, of the people who have gotten speeding tickets, what color car do they drive? Of the people that have gotten a speeding ticket, 35% of them drive a red car and 65% of them drive some other color. Is that evidence yet that people that drive a red vehicle get more speeding tickets? Well, let's look at this one more way, because I think it's still hard to tell. What if we go to the columns? I think this might be the most useful one to look at because this will actually focus on red vehicle versus other vehicles. So now I'm going to focus on columns instead of rows, and let's see how this changes our percentages. So if I come over here to this column, now I'm focused on out of red vehicles, how many have gotten speeding tickets. So red vehicles is out of 70. So I'm going to do 45 out of 70. In fact, I'm going to let you guys do it. Type in your calculator right now. 45 divided by 70. You are looking at a decimal. Take that decimal and times it by 100 to the nearest percent. What'd you get? Did you get 64%? This now means this is a totally different percentage in this spot because this was out of people who've gotten speeding tickets. How many have red vehicles? This was out of people who have red vehicles. How many have gotten a speeding ticket? Very different thing. So very different answer. Out of people who have red vehicles, how many have not gotten a speeding ticket? 25 divided by 70 times 100 is, of course, 36%, because now our columns are adding up to 100%, because these are now ratios out of columns. Let's see what happens for people with other color vehicles. So 83 divided by 150, now I'm in the other color vehicle column, and all of my ratios are coming from this original frequency table. So 83 divided by 150 times by 100 gives me 55%, which means the other one will be 45%. You can type it in and calculate it, but I know that they're supposed to add up to 100. Okay, and then this column here will be the same as this here because that was still out of 220 when we calculated it before. It's still 58% of everyone has a speeding ticket and 42% of everyone has not, so that adds up to 100. So here's the question. We have all these percents now to look at, all these ratios, all these relative frequencies. We found relative frequencies. I'm going to say that one more time. We found relative frequencies. What did we find? Relative frequencies. I hope that you guys are saying those back to me, even though it feels dorky when you're alone. I can tell when I watch your videos and you guys say things, I can tell that one of the things we do a lot better in class than online is when I say things to you and you say them back to me. We do that a lot because I need you to practice your math vocab. It's harder to do it this way. I can tell when you guys are talking to me about Pythagorean theorem and you guys say it really weird. Pythagorean theorem, okay? But I don't know, there's a lot we can do about that right now. But even if you feel dorky, when I ask you to repeat it back to me, just do it, because then you'll get your math vocab better. So all of these that we found are called relative frequencies. Relative frequencies. Okay, so the question here says, does there seem to be an association between owning a red car and getting a speeding ticket? So everything we've looked at here, do you think there's any evidence to say that Josh is correct? He's so convinced that red cars get more speeding tickets. Do you think he's right? And I'm going to let you guys take a minute. I want you to pause the video here. And I want you to write down your response to this, either yes or no. Yes, I think that Josh is right, that red cars get more speeding tickets. And then write a sentence or two about why. Or if you think, no, I don't think he's right, I want you to write a sentence or two why. Okay, pause, think, and write. Okay, so what did you think? A lot of times with these two-way frequency tables and calculating relative frequencies, you could argue it many different ways. Like some of you might have looked over here and went, hey, look, of the people that get speeding tickets, only 35% of them actually have red vehicles. This is more a question of the people who get speeding tickets, what color is their vehicle, which could apply here. I went with this one over here, which is more a question of the people who have red vehicles, who's getting speeding tickets. So I wouldn't say there's a huge statistically significant difference here, but 64% of the red vehicles were getting a speeding ticket, where only 55 of the other vehicles, which are all the colors, so that's kind of a lot more categories. 55% of the other vehicles are getting a speeding ticket. So if those percentages were really, really close to each other, if it were 64% and 64%, then I would say that Josh doesn't have an argument here. But 64% being that much higher than 55% means he might have an argument. He might be onto something. Okay, let's just look at one more example, because we don't always go through all of this. We don't always change the entire table by the whole thing. We don't do all the rows. We don't do all the columns. You can, and that's a really good way to make good comparisons on the table. But sometimes we're only looking for one specific piece of information. So just one more example down here. Let's go ahead and finish the two-way table if you haven't tried that already. To finish off this table, I'm gonna use purple here. Remember, we play our adding and subtracting game. I have this total and I have this total. I'm gonna subtract to get this total. And then I have this total of who has kids and no pets. That's a joint frequency, so I'm gonna subtract to get this other joint frequency. Now I'm ready to add down that column and get the total of who has pets. And now I can subtract across this row. 62 minus 23 is 39. And now I can add those and get 61. And then the last thing I do is just add those and make sure that total works out. So what is this data all about? Well, somebody was curious about if there's any association between having pets and having kids. So they asked adults, maybe married couples or partners or whatever, they asked them, do you have pets or not? And that became one variable, pets or no pets. And they asked them, do you have kids or not? And that became another variable, kids or no kids. Now, one of the tricky things when they ask you specifics, I actually think it's easier to figure out when you're just doing the whole table because you decide I'm doing this row and I'm doing this column. Sometimes when they ask you specific questions, that's where it becomes tricky. Like, what is my total out of? What total are we talking about here? So here is a huge tip, okay? Whenever you see this word of, I don't know if you remember in 7th grade when you did like P over 100 equals A over B and the base comes after the word of. That's true here. It's talking what it's out of. So if it says of the people who have kids, that is telling me right now that I should focus on a row. Of the people who have kids, so I should be focused on the row with kids. So this row has a total of 63. So for this question, I know it's definitely out of 63 because it's of the people who have kids. That needs to be out of something. Of the people who have kids, what is the relative frequency of having a pet? Out of this row. So I've already decided I'm in this row. So don't go picking a number from a different place. Your other number needs to come from that row. Okay, so I know 63 is my total. It's out of 63. Which of those numbers is people that have pets? 41. So 41 goes on the top. As soon as you have your ratio, you're ready to type it in your calculator. 41 divided by 63 times it by 100 and turn it into a percent. And this is the relative frequency. 65% of the people who have kids also have a pet. Okay, next question here. This one asks, of the people who do not have kids. That means I am looking at a different row and a different total. Of the people who do not have kids, that is out of 62. I always figure out my total first. It's easier to work the problem if you know which total are you out of. Of the people who do not have kids, out of 62, what is the relative frequency of having a pet? That is 23 out of 62. Change that to a percent and you get 37%. In fact, I'm even going to write those over here. That was this, it would have been in this spot going across this row, 37%. And this spot was 65%. Those do not add up to 100 because we were not focused on the pets column. These would have had to say of the people who have pets, then we would have put it out of 64. But because it said of the people who have kids and of the people who do not have kids, we were focused on these rows. Now that means we could really easily do this one too. We could say 35% because that's supposed to add up to 100. And we could also say, what would this be, 63%? That seems like a pretty even trade-off. Does there seem to be any association between people who have kids and people who have pets? I would argue yes. 65% is pretty drastic over 37%. So I would say yes, 65% of people with kids also have pets. This tells me, it seems that if you have kids, you're more likely to have a pet. because possibly you only have a pet because your kids asked you for one. Or in my case, because your husband asked you for one. So if you have any questions, please let me know. Focus in on the hardest part about this MLE is making sure you're using the right total. If it says of the people who have kids, go across the row. If it said of the people who don't have pets, go across the column. That would be out of 61. So focus on getting the correct total first, and then you'll be fine. As always, look for my feedback and email me if you have any questions. Bye, guys.